Hi, everyone. Today we're going to talk about lesson 7, which is periodic trends. And we're going to break this lesson up into two parts. So we'll have lesson 7 and lesson 8. And the first part of periodic trends is going to deal with atomic and ionic radius. So the radius of an atom and the radius of an ion. Remembering, of course, that an ion is an atom that has either gained or lost electrons. Hi, everyone, and welcome to lesson 7. This lesson is going to focus on periodic trends and specifically the periodic trend for atomic and ionic radius. If we take a look at our first slide, you're going to see, first of all, the definition for atomic radius. So a measure of the size of an atom, usually the average distance from the center of the nucleus to the boundary of the surrounding shells of electrons. So basically from the center to the outermost level. And if you notice, I've graphed all of the atomic radius data for our first 56 elements. So what we're going to do is we're just going to add some labels on here so that we can figure out which atoms are which. So I'm going to start off up at the top or at the left with hydrogen and helium. Then our second period is going to be from lithium to neon. Then our third period is going to be from sodium, Na, to argon, Ar. Our fourth energy level, or fourth period, is going to be from potassium to krypton. Our fifth energy level is going to be from rubidium to xenon. And then finally, our last energy level is going to be an incomplete energy level. We're only going to look at cesium and barium, element numbers 55 and 56. So a couple of things that I would like you to notice. Number one, if you look across a period, so hydrogen to helium, lithium to neon, sodium to argon, potassium to krypton, you will notice that the atomic radius gets smaller. So we're going to talk about why. The other thing that I would like you to notice is if you look at a group. So let's say we look at group 1 on the periodic table. So we have hydrogen, lithium, sodium, potassium, rubidium, cesium. Notice that their atomic radius increases as we go down a group. And we're going to talk about why that is. So let's summarize both of these trends. So the trend within a group from top to bottom is we're going to say that atomic radius increases. I'm just going to make this a tad bit bigger here so we can see it. So atomic radius increases. And there are two reasons why atomic radius increases. So the first reason is this. As you go down in energy levels, so from first to second to third to fourth, we keep adding shells onto the outside of our atom. As we're adding shells on, we're increasing that distance from the nucleus to the outermost electrons. So atomic radius is going to increase due to an increase in the number of energy levels. There's a second reason why atomic radius increases, and that is due to something called electron shielding. So there's an increase in electron shielding. Now let's talk about what electron shielding is. So if you look at this diagram of an atom, you have a valence electron, that's the one that's out here, where it says outer electrons, and then here in the middle you have your nucleus. As you increase the number of inner electrons, they begin to act as a barrier. So if I look at the number of inner electrons here, see this inner energy level, notice that it's blocking the outermost electron from being attracted by the nucleus. So those inner electrons, electrons that are occupying inner energy levels, act as a barrier between the nucleus and the outermost electrons. And that ends up allowing that atom to kind of stray a little bit further away. And as a result, the atom gets larger. So when we look at why the atom gets larger going from top to bottom, we're going to identify those two as the cause. Now, let's take a look at, so I'm just going to label our arrow here so we can summarize this. So we're going to say atomic radius increases going down from top to bottom. And now let's take a look again at the trend going across a period. So this trend going from lithium to neon is that it decreases. What I want to do is make this a little bit easier to understand. So we're going to talk about everything increasing. So atomic radius is actually going to increase going from neon to lithium. So that's right to left across a period. So what we're going to do is we're going to add some text here. So we're going to say atomic radius increases. Notice up here I've identified right to left. So that's going to be increases again up here. And the reason for it is a little bit more complicated. So number one, you're not changing energy levels as you go across a period. So if you look at an element like sodium that has 3 energy levels, if you go all the way across the table and look at an element like argon, that also has 3 energy levels. So there's no change in the number of energy levels. Instead, what happens is that the nucleus on the right side of the periodic table pulls in those atoms tighter because there are more protons. So we're going to say a stronger nucleus is present on the right side of the table. And this is due to an increase in the number of protons. Or what we're going to call a greater effective nuclear charge, which we can abbreviate as ENC. So the nucleus essentially is getting stronger. As the nucleus gets stronger, it's able to pull in those electrons tighter, so we see a decrease in the size of an atom. So if I were to draw a circle that represented the size of an atom, on the left side, I would make my circle fairly large. And then as I go across, the circle would actually get smaller and smaller. And then eventually when I get all the way over here, the circle would be really small. So when we talked about why atomic radius increases or decreases across a period, we didn't mention the number of energy levels because that doesn't change. And we also didn't mention this new term, electron shielding, which we just learned about. And the reason is electron shielding remains the same within a period. So if we go and look at the next slide here, I have 2 atoms that are in the 3rd period, sodium and chlorine. Sodium has a total of 11 electrons. Its atomic number is 11. And it has 10 inner electrons and 1 valence electron. If we look at chlorine, it has 17 electrons, but it has the same number of inner electrons, also 10, because the rest of the electrons that it gained are all valence electrons. Because it has the same number of inner electrons, we're going to notice that the electron shielding doesn't change as you go across a period. So we're never going to use electron shielding as a reason unless we're talking about changing elements within a group. So going top to bottom in a group or a family on the periodic table. We are not going to use that argument for moving across a period. So now that we have finished talking about atomic radius, we're going to begin to look at the ionic radius. So before we do that, we need to learn a new term, and that term is isoelectronic. So I wrote up here, what does it mean for an atom and an ion to be isoelectronic? And it's a very simple term, although it's quite difficult to understand. It means that it has the same electron configuration. So let's take a look at an isoelectronic series. So the first one that we're going to look at is with neon. So if I type in the electron configuration for neon, so I have 1s2, 2s2, 2p6. Now, if I look at the electron configuration for sodium, we're going to see how it's similar. So 1s, 2, 2s, 2, 2p6, 3s, 1. However, we don't have a regular sodium. We have a sodium ion. That plus charge means that it has lost its outermost electron. So in order to show that, we're going to draw a line through this outermost electron to show that it became an ion. Notice that when it loses that electron, it now looks exactly like neon. Let's try that with magnesium. So we're going to begin by writing out the electron configuration for magnesium, the full atom. So here we have 1s2, 2s2, 2p6, and finally 3s2. However, we don't have regular magnesium, we have magnesium ion, so those outermost electrons are going to be lost. So this goes away, and now we have a magnesium ion that looks identical to neon. Let's take a look at oxygen. Now, when oxygen forms an ion, it does not lose electrons like sodium and magnesium. Oxygen is a nonmetal, so it's going to gain electrons. So if I write out the electron configuration for oxygen, I have 1s2, 2s2, 2p4. However, we have oxide, the ion, which has gained 2 electrons. So when this gains 2 electrons, this 4 is no longer there, and instead we have 2p, I'll move it over a little bit here, we have 2p6. So gaining 2 electrons changes that 4 up to a 6. We could do that one more time. So if we look at fluorine, fluorine has the electron configuration 1s2, 2s2, 2p5. And when we add 1 electron to fluorine, so we're going to get rid of that 5 there, we're going to add 1 more electron, and that becomes 2p6. And now it too looks exactly like neon. Here's the thing. Even though they are all the same electron configuration, they all have different numbers of protons, so they don't become neon. It just means that they have the same electron configuration as neon. They have the same number of electrons as neon does, but they don't have the same number of protons, and they don't have the same properties as neon does. The other part that I want you to think about is size. So if we look at the size of each of these, the size of neon is going to be right in the middle. And the reason is neon has 10 protons and 10 electrons. The size of magnesium is actually going to be the smallest. So down here, we're going to write magnesium with a 2+ charge. We're going to say that this is the smallest in the group, and the largest in the group is going to be oxygen. So up at the top here, we have oxygen with a 2- charge, and we're going to say that that is the largest. Now, what makes one small and one large if they all have the same number of electrons? Well, it has to do with their number of protons. So in the case of neon, we have 10 protons holding on to 10 electrons. So 10 protons and 10 electrons. In the case of oxygen, we have only 8 protons holding on to 10 electrons. And in the case of magnesium, we have 12 protons holding on to 10 electrons. In each case, we have 10 electrons, but the atom, or in this case, the ion that has the greatest number of protons is going to pull that atom in nice and tight, so it's going to end up being the smallest. And the ion that has the least number of protons, that's up here at oxygen, that is going to end up allowing that atom to expand because you have 8 protons holding on to 10 electrons. We give this a special name. We call this the proton to electron ratio. So up here, when we look at O with a 2- charge, we have a low proton to electron ratio. And if we look at the bottom here, we have a high proton to electron ratio. So oxygen ends up being the largest ion because it has the lowest proton to electron ratio of this group. And magnesium ends up being the smallest because it has the highest proton to electron ratio, and it's able to attract those outermost electrons very strongly. So adding a trend for atomic and ionic radius tends to be a little bit tricky. So what we're going to say here is within a group, nothing changes. So within a group, we're still going to say that it increases. So ionic radius increases, still top to bottom. Why? Same reason. Energy levels are added. And the second reason is more electron shielding. Now, the trend across a period is kind of weird. So to draw this in, we're going to say that the ions get smaller at first. So it looks like this. Then suddenly they get bigger and then smaller again. So let's remember why that's happening. So on the left side of the table, we have metals. Metals lose electrons when they become ions. So as they lose electrons but gain protons, they get smaller. So at first, it's going to get smaller, 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 smaller. Then when we get into the nonmetals part, remember that nonmetals gain electrons. So the nonmetal that gains the most electrons is going to be one that has 5 valence electrons. It will gain 3 electrons. The one that has 6 valence electrons will only have to gain 2 electrons. The one that has 7 valence electrons will only have to gain 1 electron. So what starts off big again starts to get smaller as we head toward 8 valence electrons. So that is extremely confusing, but we're going to work through a couple of problems and draw some of these out, which hopefully will make it a little bit easier for us to understand. So we're going to say left to right, ionic radius decreases. For metals, as the charge on the metal increases. That's happening because more electrons are being lost. And then suddenly, ionic radius jumps up for nonmetals, and then decreases once more as fewer electrons are gained. Again, the reason for this is metals will lose valence electrons until energy level empties out or is empty. And then nonmetals will gain valence electrons until the energy level is completed or full. Okay, if you have questions about what we just discussed, please make sure to stop by office hours and I can try and help you work through any questions that you might have about atomic radius or ionic radius. Thanks, everyone.